Hello, everyone. Thanks for joining. Today's talk is by Andrey, CTO of Qdrant, and we are going to discuss quite a lot about vector search and applications. After the initial talk, we'll have Q&A. So we'll reserve all your questions for that. And just to give a very quick introduction about myself, I'm Ramsri, currently based out of Hyderabad, India. I run learnnlp.academy, where I teach natural language processing courses. And I have two NLP-based SaaS products, Question.ai and Supermeme.ai. And especially for Supermeme.ai, we have built vector search for searching memes with emotions. So I'm very familiar with the area of vector search and vector embeddings. And I wouldn't waste any more time, and let's get started right away. Let me hand over the screen to Andrey. First of all, thanks a lot to agreeing to take this talk, Andrey. And
thank you. I'm very pleased to be invited, actually. So just a short introduction from my side. I am Andrey. I am a CTO of Qdrant company, and we position ourselves basically as a metric learning, similarity learning company. We are focusing in this area where we see that this technology could be utilized more in industry, and our efforts are focused on making similarity learning practical and available for all companies and developers out there. We are heavily involved into open source movement. Our main product is a Qdrant vector search engine, which is open sourced from day zero. It's available on GitHub and already crossed the line of 2,000 stars, which is pretty good for this type of products, which targeted more on core development teams and machine learning engineers. It's written in Rust, as already mentioned by our viewers, and actually this language gives us possibility to make it very fast and very scalable from the day zero. It's easy to use. It supports both gRPC and REST interfaces, so you can access it even from your browser. Basically, you do not even need to know how to code to give it a try, actually. And it supports filtering on top of similarity learning, also from the day zero. It was like its main feature, and the whole architecture is designed that way that it makes this filtering very robust in practical applications. I started this project basically as a pet project to solve my problems at work. I was also working on a couple of projects. One of them were e-commerce search, other was a job matching search, and I struggled a lot in combining the vector similarity with some filters and business logic business required during the development. For example, in e-commerce, we were building a search based on the map, so user should be able to select like specific regions, like city or street, where he wants to search for the product. And this type of filtering at that time were impossible to combine with traditional libraries used in vector similarity, and that's why I started to think about bringing this functionality into some form of engine. And thanks to actually Corona lockdowns, I got the time to actually program it and made the first version. But let's maybe talk a bit about what similarity learning even is. I guess the most simplest explanation here would be that we have some encoder, some model, some neural network, which can convert our objects into embedding space, into vectors. And these vectors have the property that for similar objects, these vectors are close to each other, and they're closer to each other than to some dissimilar objects. For example, vectors of two cats should be closer than vectors of cat and dog, as you can see on this simple example. And it's important, I guess, to mention that similarity learning and similarity search is not only about search as search in Google. It's not necessary that you need to type some keywords into some input box and get the results. Actually, the search as a technology itself used in very different applications, starting from recommendation system. It could be a similar image search. It could be also the regular search that you can use in Google, but it's only one application of the technology. We also discovered many other interesting applications. For example, chatbots are usually built using the intent detection, and intent detection is also could be implemented as a search algorithm. Also matching engines, all sorts of content recommendation, and also the one interesting case is anomaly detection, where you can use similarity learning to find outliers in your distribution. But what makes similarity learning so interesting compared to the traditional approach like classification? And I think that the biggest impact and the biggest reason why similarity learning is much more usable in real life than traditional approach is actually breaks down to the fact how we label our data. In traditional classification, you have a set of objects, and for each object you need to assign some label. It could be like image of cat, and the label that says that this image actually contains a cat or a dog. But in similarity learning, it's a bit different. In similarity learning, we do not require to have a strictly defined set of labels. Instead, we only need to have some understanding of which objects are similar and which objects are not similar. And this actually gives us a lot of opportunities in terms of usage of data. For example, any classification data set are actually also a similarity learning data set, because the information about classes could be interpreted as information about similarities. If two objects have similar class, then same class, that means that in some cases they are also similar. But it doesn't work in other direction. You cannot use a similarity data set to train regular classifier, because you might not even have this information. And this actually gives a very interesting opportunity to combine multiple before incompatible data sets into one large similarity data set, which could be used to train more robust models. For example, in area of job matching, there are a lot of different approaches how to categorize all jobs. There are even several standard ontologies how to assign different roles to positions. And those ontologies are rarely compatible between each other. For example, for front-end developer role, you would have a developer label in one one ontology, and front-end developer in other, which looks similar but not identical. So you cannot actually train any classifier based on both of this data. You need to choose one, and you either need to label all your data, or you need to limit the training set to only one of them. But in similarity learning, you can combine it, and you can use both at the same time without very small effort. Moreover, similarity learning encourages you to use self-supervised approach. If your data combines of multiple components, for example, if it's image of some item and textual description, you can already use it to train the model. You don't even need to label anything. You just ask model to compare text and image. And as we know which text assigned to which description, we already basically have a pretty large data set of items on Amazon or whatever e-commerce store you have. Apart from that, similarity learning allows you to do some tricks you cannot do with traditional approaches. For example, it's what I call a neural rules. Is an approach where you can manually make changes in your reference set so that further classifications will be more accurate. And unlike classification, it won't work only for some specific cases where you can say that this exact role doesn't fit our description, but it also allows you to define area of effect of your rules, and it makes the work of people who maintain the system in real production much easier, because they have an interface to manipulate predictions much more flexibly than they could do with this just classification and hard-coded rules. Yeah, and another part of similarity learning, as I mentioned before, is models themselves. Today is usually already enough for the baseline to just download some pre-trained model from Hugging Face, install it, get vectors, and already without any training, you will get pretty decent performance with a search or whatever task you're trying to do. But in some cases, you would like to have more accuracy, more precision in your model, in your search. And this is where you actually need to spend some time and resources on improving the model. And our second product, Quaterion, allows you to do it very quickly. Basically, what we did there is we implemented the pipeline focused in metric learning tasks. It focuses on losses, which are usually works with metric learning, like triplet loss, like contrastive loss. And we build a caching mechanism on top of this pipeline, which allows you to only encode your data once and then reuse it on each epoch of training. And if you have some limited amount of data, even this limited amount of data is enough to train the final layer of the model. And with caching, you can do it basically on your laptop. You won't even need an expensive GPU, because the training of the last layer of a huge model is very cheap. And you can do like dozens of experiments in just 1 hour. and you can see how it's progressing compared to pre-trained model, and actually it gives you an understanding how similarity learning actually works. It has some features, or I would say rather some pitfalls you could get into if you try to apply just regular patterns from regular training of classifiers. So it's very important to take your hands on some example, and if this development cycle is very short, you can see the results from your experiments in just minutes. You get used to similarity learning much faster, rather than if you were training the whole model for hours or days before realizing that you did something wrong in the very beginning. And that's actually the superpower of our framework. It allows you to enable this fast computations with just a single configuration line. And after you feel confident with your model, you can disable caching and make a full training cycle in a regular way and achieve even better performance. Yeah, it's built on top of PyTorch Lightning, so it handles all the distributed training for you. You do not need to worry about anything, and you only need to watch how your model trains very fast. That's basically all my intro talk. I'm happy to discuss these things if you have any questions.
Awesome. Thanks, Andrey, for the lightning talk, and happy to we can take questions from the chat. And so whoever has questions, feel free to ask them in the chat, or you can raise your hand and we can bring you on the main stage. Awesome. So before that, I think I can get started with questions, Andrey, as people are typing already.
Sure.
So one thing is, if I understand Quaterion, what you have built for similarity learning,
yeah,
you take, let's say, sentence transformers, and then you can fine tune sentence transformers on top for the data set that you have with just few lines of code as well as few samples. Is that a good statement to say?
Yes. We train like in the default configuration, we only train this final layer of the sentence transformer. So the training itself is really fast, and we do it in a way. We have a collection of head layers actually, and we are trying to preserve the capabilities of the original model. So we do not fall into this catastrophic forgetting for the neural networks. We use a skip connection layer, for example, and at the beginning of training, you already have all the signal from the original encoder, and we try to not corrupt it in any way. So all the trainings happens as an addition to the original model and do not overwrite it, I would say.
Got it. And so perhaps we can stop sharing screen. Sure. I think that's easier. People can see you. And so Raj asks, can this be extended to cover pretty much all types of recommendation engine use cases? Any limitations?
Yeah. Speaking of recommendation engines, there are basically two historical approaches in recommendation. The one is interaction-based or history-based, where we try to predict what user will like based on its interaction history with the system. Like, For example, if you are using Netflix, Netflix asks you which movies you watched before, and it tries to predict which movies you're going to watch next and which movies you're going to like next. And the second approach is content-based. So we, instead of looking at history, we can look at similarities between movies themselves. Like if it's the same actor playing in this movie, is this the same director? Is it the same genre? Is it the same I don't know, country which produces the movie? And based on this, we can find similar ones. And I guess the key to successful recommendation engine is actually a combination of both. So you would need to take into account the similarity between data and the similarity between behavior of your users. But if you are going to start, I would say it's better always to start with content-based recommendation, because in this case, you do not need to have a large history of interactions with your system. You can start, even if you have 0 users, you can already build something, at least a baseline, which can give a reasonable performance on your data.
Got it. And Moz asks, does this work for all languages? Is it multilingual?
Yes, it's actually a very good point here. There are models which are able to convert sentences from like hundreds of languages into same vector space, so it can find your query results even if you type it in a different language. So, for example, if you're looking for some product and you type like laptop, it will find laptop in every language you have in the model.
And Dimitri asks, great talk, Andrey. Do you have experience applying similarity learning to multimodal settings? For example, fine-tuning clip for an e-commerce domain?
Yeah. Hi, Dmitry. Yeah, we're currently working on some examples, some demos using clip model. It's not public yet, and yeah, the results are not yet there, but we hope that we were able to also fine-tune clip model for using Quaterion, of course, for some custom domain as well. Yeah, same way as basically we have already fine-tuned, for example, question answering model or image recognition model. And it's work in progress. Yeah.
Awesome. And Deepanshu says, not a question, but would like to congratulate Andrey and team for the contributions. And he has been an early user of Qdrant. Awesome.
Yes. Thank you for your help, for your contributions in Qdrant as well. I guess we had a lot of we fixed a lot of bugs based on the reports from community.
Awesome. And Raj asks, would this be able to handle structured data as well? If so, how does that happen?
Yeah, that's actually a very reason why I started building Qdrant in the first place. I had this problem of combining similarities and structural approach. I have already talked about example of retrieval based on map of location, geolocation data, but there are also other examples in area of job matching, for example, like apart from similarity between different positions, we also have a lot of additional information like location of candidates, like spoken languages, like career expectations, salary expectations, and so on. And all of this data it's pretty hard to encode directly into neural network. You usually just do not have enough data to train such a model. So in this case, you can still use similarity learning. You can still use similarity between job titles, but on top of it, with Qdrant, you can also apply filters. So for example, if you want a candidate and job position to be in the same country, you just make this filter and it will automatically exclude all non-relevant jobs or non-relevant candidates from your search. Yeah, and that's basically how we approach this structural data problem. And actually, it actually happens a lot. This situation where you need to apply filters is actually very frequent. And if you just think from a academical perspective, you would rather think about how to scale the solution, how to make a search for 1 billion vectors instead of 100 million. But in real life and practical applications, you rarely need so much vectors, but you need to operate with whatever you have very precisely. And I can give you another example. We actually have a bunch of demos on our webpage. And one of these demos is a search of similar dishes in restaurants. We crowd food delivery service here in Germany. And we use these photos of food to make basically a recommendation. So you could click on whatever dish you like, and it will automatically suggest you something similar. But it would have no practical purpose if you're just looking for similar food. You can go to Google and make this request. What makes this application actually usable is the ability to provide your location. And in this case, system will automatically recommend you only those dishes which are served by a restaurant within your delivery area, within your delivery radius. And in this case, you can actually search for food you can actually deliver. And without this feature, it just makes no sense to just show you what you cannot eat, right?
Got it. So let me take a step back and ask the questions most beginners would have. So at one end, you have Elasticsearch and Solr and things like that, right? And they have also introduced vector embeddings. Now, my question is, from a beginner's perspective, when Elasticsearch, Solr support vector embeddings, what are the other players doing in this space and how do they differ?
Yeah, so Elasticsearch is a great product. If you're working with text, if you heavily rely on text search, if you have this box which says import your query, then of course you would use Elasticsearch in some or another way. But as we have already spoken, the area of application for vector search is much larger than just text search. And Qdrant as a product focuses specifically on this area. This is why we're actually able to perform this search much faster and much more accurate than Elasticsearch does. And we are not limited in text. But yeah, the best practice would be, I guess, if you're running this Google type search engine, is to combine both keyword-based search and semantic search. Also, the performance, if you actually know what you're looking for, if you know exact keyword, the full text search, Elasticsearch will work better for you. But if you are just exploring, if you're in a process of discovery something, or you're running like a matching or recommendation, in this case, you just won't have these keywords you're looking for. And in this case, vector similarity works better.
Got it. And just a follow-up on that, does Elasticsearch do similar nearest neighbor comparisons across the vectors? And secondly, is there, simultaneous filtering like most of the libraries do?
Yeah. Yes, the main idea is the same. You have some embeddings and you do the search. The difference is, of course, in architecture and implementation. And for Elasticsearch, it's just not the main focus of the engine. They have a huge legacy code base. They're doing a lot of stuff. They're supporting a lot of legacy features they have. For that reason, they just not able to implement it as fast as we can. And we are working currently on benchmarks, of course, to prove our claims. Yeah, but but if you just give it a try, you will see the difference is dramatic between Elasticsearch and basically any specialized search engine, not only us. Yeah, and another point here is support of filtering, and it's also a big difference between how Elasticsearch does this handles the filtering. So basically, the main difference between keyword search and similarity search is that whatever object you have, you can assign similarity between any pair of objects. Like you cannot draw the line that we should stop after similarity drops below 0.8 or some other data, because all different models will have these different thresholds, and even within single model, you could have examples where the search performed correctly with low scores, and where search performed incorrectly with very high scores. So for this case, you cannot make a cut of your search result, and that's where actually filters gives you a headache, because you cannot do post filtering without using results. You cannot retrieve like top 10 vectors and then apply filters. You need to do it during the search. And for that reason, the architecture of this payload storage, of this metadata, should be very close to the storage of vectors. So you should be able to make this comparisons during the search in the HNSW, and therefore architecture of legacy search engines just do not allow them to develop it in efficient way.
Got it. And does Elastic use HNSW as well? And I understand that the CRUD operations are much faster with the rest of the vector search engines, right? So does Elastic use HNSW?
Yeah. HNSW is like a general name of the algorithm, but each of the engine, I guess, already have a custom implementation of HNSW. For example, we implemented our own version in Rust with this support for real-time filtering on the search phase. Built in directly into the algorithm. So you cannot just take HNSW lib from GitHub and wrap it into some API. It just won't work. Yeah. And the main pay here is actually not in building the algorithm itself, but combining it with all payloads, combining it with the ability to update it dynamically. And overall, the HNSW is very hungry for CPU when you're trying to build indexes. Why you should handle these updates very carefully.
Got it. Okay. And Mohanandi asks, thanks for the talk. It has all the preferred features like uses Raft, gRPC implementation, etc., which Solar or Lucene lacked and we wanted. Lucene 9 and onward has the vector search now. Do you see this as a potential competition for Lucene, or will it just stay a vector search only?
Which one?
Mohanandi asks.
Lucene, it was implemented as a part of effort of Elasticsearch to actually introduce vector search inside the core, but the benchmarks that doesn't look well for them.
Okay. So Kiran asks, what algorithm does Qdrant use for vector search? Any benchmarks in performance when compared to other providers?
We currently have benchmarks for our own engine. It's available on the GitHub, but we are also working on comparison between engines. And we expect a lot of criticism from this area, so we are trying to make it as good as possible.
Got it. And Raj asks, you got Inception from NVIDIA, and how is that going?
We're currently not focusing on model training just yet. We are more focused on the database part of the engine, on the distributed deployment, on the scaling, on the high availability. That's our priority for now. After that, we are also planning to go deeper into optimizations like product quantization to also make it possible to serve a huge amount of vectors with some minor drawback of quality. For some developers, for some users, it is also an interesting feature to have.
Got it. And next question is from me. So one thing that I wanted to understand is that, do any of the vector search engines, or can we build a vector search engine to support multiple embeddings at once? Why I'm asking that is, for example, let's say for meme search that we have built, we have for every meme, we have, let's say, 2 or 3 descriptions. It's almost assume that you have multiple image captionings. And for me, the thing is that there is an input query. All I want is I want to get the max match between the 3 embeddings, and I just want to retrieve that. Right now, the problem is that I need to store metadata multiple times and all those things. So it's a pain. So I'm thinking, what's the best solution for this?
It's of course possible. And we are currently working on it. Hopefully it will be a part of our major release, version 1.0. This feature is actually requested many times, so we are going to prioritize this.
Got it. Awesome. And what other use cases have you seen where you need to store multiple embeddings for a single, row?
Another case would be if you are doing image recognition and you have one image, but you are using the segmentation, so you have multiple selections on a single image. And in this case, you are interested in finding the best match among a single image, and you have also at the same time multiple images in your database. So in this case, you would have like not a fixed amount of vectors per record.
Got it. Okay, I think that makes sense. I have tried exploring to see if that's possible, and I haven't really found a strong vector database that supports that, but glad to hear that. And one of the other question that I had was, so right now, if you go to SBERT, sentence transformer supports fine-tuning as well. So whatever you introduce, Quaterion, how does that differ from the baseline that they provide?
Usually if you're going to train SBERT, you will need to train it like completely from very beginning. Or if you are going to use this frozen layers, you need to do it manually and rely on your GPU. Because the main difference, I guess, between training a regular classifier and similarity learning model is that the batch size in similarity learning is much more critical than in standard classification. You would need to have as large batch as possible, because you need to find negative examples for your loss function. In case of triplet loss or contrastive loss, you can have a positive pairs in your training set, but in order to train it properly, you also need as much negative examples as possible, as many as possible. For example, in our demos, we trained a model for recognizing cars, and we use a batch size of 2048 something on a laptop, and it's just impossible to have this large batch if you use traditional pipelines which perform a full inference for each step. You just won't find that huge GPU, or it will cost you a fortune.
Got it. Okay. So the other question is slight change of pace, thought. There are already few companies who got a head start in vector search, right? So, and I believe Qdrant is kind of a new player in the game in the last 1.5 years. So how were the discussions with VCs and how did the fundraise and all those things? What was your experience from there?
Yeah, of course, yeah, we are not the first one, and I guess when we just started, it was only Milvus which were available for vector search as a service, but now there are already several specialized on vector search, and of course some larger players are trying to integrate vector search capabilities into their existing product. But I guess the best factor of our progress is our progress in our roadmap. We were able to implement a huge list of features in just half a year. We are operating as a company only half a year, and at this time we are getting very close to the full enterprise level of production. So I guess it will take us only a few more months to implement proper replications in our distributed deployment, and they're good to go.
Okay. And just like to potluck, people bring their own flavors. So if you see the vector search space, what do you think is the biggest flavor that Qdrant adds? What's the focus?
Our approach here is that we allow you to build your application from very low level. We do not force you to use any framework. We do not force you to train your model and convert it in our format. We do not force you to write plugins for our system. Instead, we serve as a standalone engine, and you build your application around us. So it's a big deal for companies which already have some code base running in production, and for them it's much easier to use plug-and-play solution rather than inventing everything from scratch and trying to serve models inside database or something like that.
Got it. Great. And personally, when I built vector search, when I was solving vector search problems, what I realized was that there are quite a lot of on the top of vector search things that you need, which could be, if you're doing recommendation engines, either the diversity ranking or aggregations, or you have weight scores combining multiple outputs, etc. Right? So what I meant to say is that whatever Elasticsearch and Solar components that are there, at the end of the day, on top of your vector search, fast retrieval and CRUD operations, you have to do some level of those aggregations or weightage things, or it could be other things, right?
Like rescoring, yeah.
scoring, re-ranking and all these. So
Yeah.
do you see like most vector search engines evolving into the full suite of tools, toolkit?
This what actually I do not like and trying to avoid in Qdrant at all costs. Yeah, because in this case we will need to invent our own format for serving this post-processing models, and yeah, imagine if you need to do an extra work to just support this. This plugins basically in Qdrant. So from my perspective, it's much better to have a plug-and-play solution. You might think about it like a microservice which you can run, and after that, there are plenty of possibilities for you how to post-process the result from Qdrant. And we are trying to deliver the fastest and most scalable solutions there, so you won't be limited in these plugins or this post-processing components. You would be able to do it on your own part of the code, and you will be able to do it in a way you would like. Because if I say that we invented like universal format for post-processing, it would be a lie. I think it's just impossible to do. And I saw so much different approaches here, so I'm trying to not even interact with this.
Got it. Okay. And Raj asks, any resources that you can recommend to understand vector search better so that we can start identifying use cases and start using the product effectively?
Sure. Best resource is our landing page. Yeah, I actually have quite a few articles on the topic. We have a tutorial if you want to start building your vector search solution from scratch. We have some theoretical articles on how to train models on the triplet loss. We have a lot of descriptions how metric learning could be applied in different use cases, for example, in anomaly detection, in image similarity, and so on. Yeah, and of course, join our Discord. I'm answering all the questions there.
Awesome. Great. So I'll finish off with by asking a last question of mine, and if we have time, we can take more from others. So basically, I wanted to understand the high-level pipeline to train a, let's say, a classification model for something out of domain. For example, let's say you take a regular SBERT model that's not trained on medical data or legal data. Now, there are two aspects to it, right? One is you need to fine-tune the similarity model, then you need to fine-tune the classifier. How do you combinedly do that? And what is the pipeline if you have, let's say, new legal data classification or medical data classification?
Yeah. So if we are talking about like real life example here, I guess the best thing you can do is to start with just pre-trained model and see how it works in your case. If it's a medical, let's say it's a medical chatbot, then you probably should have some database of question and answers. So if you already have question answers, you can use it as a test set for the model. If it can identify proper answers to questions out of the box, it's already a good model. So and most importantly, you need to measure. In order to improve something, you need to have some measurements. If you do not have this label data set, I would recommend to start with just labeling at least something, at least amount of data you can label in one evening. It would be around 200 samples. but it is already enough to at least measure the efficiency of your solution. And in some cases, it's even enough to fine tune it. I saw examples where the 200 samples was enough already to make a pretty huge progress in accuracy and precision of the search. Yeah, after that, of course, you can look at fine-tuning libraries. I would recommend to start with just a small amount of data and small head layer. So do not try to rush into fine-tuning the whole model for medical domain or something like this, because it will take a lot of resources. It would take a lot of time, and it is possible that you are going to be frustrated much earlier than you can achieve some significant results. So my approach is always to start with simple and fast to implement steps, rather than rush into full training or anything. Yeah, if you need a classification instead of just search, then in this case you would need to create some reference set, like if you want to classify new symptoms for some disease, then of course it won't give you any predictions if it have never seen anything like this. But the advantage of similarity learning is that you won't need to retrain the whole model if you need to add some new symptoms into your collection. You only need to have a set of references. You need to encode these references into vectors, put it into a search engine, and then when user comes to you, it will see which looks similar to what they have.
Got it. Awesome. And Adil asks, you mentioned it can store any form of data, text, images, etc. You should generate some embeddings from data. How do you determine the size of these data?
And I don't think I get a question. Yeah. So I'll try to answer. Yeah. Basically, Qdrant itself does not import data for you. This approach we selected from the start. So we do not do not try to do everything. We are solving the specific task, but we are doing it very well. And this task is storing, managing, and searching for embeddings. So whatever model you have, you can use it to encode your data. The size of embeddings is defined by the model you choose, and then you upload your embeddings into Qdrant.
Got it. Awesome. I think we don't have more questions in the chat, and yeah, we are right on time. So any closing thoughts from you, Andrey?
Well, I encourage you to try vector search. It does not require any specific knowledge. If you just want to play around with it, you can use pre-trained model. You do not need to train anything. Yeah, and once you see an example in your day job and your daily task, which could be solved with similarity learning, let me know. Maybe we can help you with that.
Awesome. Yeah, and thanks a lot personally for taking this talk and educating the audience and answering all the questions. I will personally, explore Quaterion and see more of it, and I'll reach out to you if I have any questions.
Sure. Awesome. Sure. Yeah. Happy for all feedback, especially bad feedback, because we can improve in this case.
Awesome. Thanks everyone for joining, and have a great day.
Thank you.